Section 2.3, Calculating Limits Using the Limit Laws, Objective 2. In this objective, rather than using direct substitution, we are going to evaluate limits at problem points. What this means is that we are going to have to employ alternate methods. We'll be looking at things graphically, analytically, and using what's called the squeeze theorem to find limits when our direct substitution doesn't work. So when you're done, I'd like you to be able to discuss how you decide which alternate method is appropriate. So before we get into this, you have to know that there are three types of problem points for which you will need to be finding the limits. And you'll notice that these problem points are very closely linked to all the domain issues that we had in earlier sections. So the first thing that you will have to deal with are removable problems, or holes. And if you recall, those problems appear when you try to divide by 0. And usually you can recognize these when you have a numerator of 0 at the same time that you have a denominator of 0. The second type of problem is if you have a joint on a piecewise function. Now sometimes piecewise functions are written explicitly with the curly braces designating your branches, and sometimes they are written in disguise. So you need to realize whenever you see a piecewise function in disguise and you are interested in the limit at the joint, you will have to create a piecewise function written in normal notation in order to work with it. Thirdly, we'll have problems that cannot be fixed. Now these will come from division by 0 when you end up with oscillations or asymptotes, and most of these happen when the numerator does not become 0, when the denominator does. Here with type 1, example 1, we're going to be dealing with problems that generate holes for us. So if we look at part A, we can see that we have a limit as x approaches 2, and we're going to always try direct substitution first. That is our first line of defense. And if I plug in a 2, I will get a 2 squared minus 4 gives me a 0. And on the bottom I'll get a 2 minus 2, which is a 0 on the bottom. So this is evidence of a hole. Typically when you get a 0 over 0, it will end up being a hole. That's not always the case, but most of the time it will be. So if I were to graph this on my calculator, we could see that the limit as x approaches 2 of this x squared minus 4 will look an awful lot like the limit of an x minus 2 times an x plus 2 over an x minus 2. Notice that these two are the same. So this expression will equal the expression x plus 2 as long as we are not at 2. And since the limit deals with values of x that are close to 2 but not equal to 2, we are able to eliminate the problem that was creating that hole and then compute the limit using direct substitution. So if we verify this graphically, we can see that the graph of this expression is going to look exactly like the graph of x plus 2, except at 2, which was a problem in the original function's domain, we will have a hole whose y-coordinate is the same as the limit. So I can connect those together and end up with a graph where if I jump to the left and right of 2 and move along the curve toward that 2, I'm going to hit the limit of 4. So notice that the coordinates of the hole are the x value we were approaching in the limit, and then the y coordinate of that hole is the limit itself. So let's look at part B. Part B, again, remember your first line of defense is to try to plug that in and do a substitution method. Just do that direct substitution. If I plug in 0, I'll get a 4 squared minus a 16 over a 0, which simplifies to 0 over 0. Anytime I get that 0 over 0, I have a very good candidate for a hole. So if we look analytically, I can fix most holes, we'll get into other kinds later, by creating factors that eliminate the problem of division by 0 on the bottom. So looking at this right now, it doesn't look like I can cancel out an h with the top because h is not a factor of 16. So what I need to do is multiply this out. Remember, we can write that 4 plus h twice and then do our distribution or our reverse foiling. And then I can subtract that 16 at the back. When I do this, I end up with the 16s canceling, and then the top will have an h in common. As soon as I can pull out that factor, I can reduce it from the top and bottom. And the reason I can reduce, remember, is that limits deal only with expressions near, or values of h near 0, not at 0. And this is equivalent to 8 plus h, as long as h does not equal 0. By doing this process, I have eliminated the issue that was causing me to divide by 0, which means when I plug 0 in now to the fixed issue, I end up getting just a plain 8. We can verify this graphically by graphing the line, or the expression, y equals 8 plus 8x. And at 0, we're going to have a hole. But the slope is 1, the y-intercept is 8. Notice again that if I jump left and right of 0 on the curve itself, and I travel toward an x value of 0 from both sides, I'm approaching that y value of 8. So I have coordinates for the hole that are the x coordinate I'm getting close to, and the limit result. We have one more type 1 example, and the reason we know that this is a type 1 is that if I plug in that t equals 0 to both the top and bottom, I'll get the square root of 9 minus 3, which is 0, over a 0 squared. So again, I've got that 0 over 0, which means it's a good candidate for a hole. To verify that it's a hole, I need to be able to fix the problem, which was causing me to divide by 0. So that means somewhere through analytical algebraic techniques in my tool bag of algebra skills, I should be able to create a factor of t squared on the top so that I can factor and reduce. So in order to do that, we have to stretch all the way back to our pre-calc and algebra 2 classes and think about when we rationalized fractions. When we did that, chances are very good that you thought about rationalizing with a conjugate. Now remember that when we are working with expressions that are not equations, we can only do things to the expressions that do not change the value. That means we can add things that equal 0, or we can multiply by things that equal 1. So in this particular case, we are going to make a very smart choice for 1 that helps us get rid of this radical, because it's the radical that is keeping us from canceling this t squared, because this t squared is up inside the root, it's trapped. We can't get rid of this one unless there's a t squared up here that is outside of the radical. So I'm going to ask that you remember that conjugate concept that you did last year, and with that, remember you had your two terms and you simply changed the sign in the middle. By doing this, we are multiplying by something that equals 1, so we are not altering the value of this expression, we're just making it look better so that we can work with it. Now if you recall, the reason conjugates are nice is that the first times the first gets rid of the radical, then the outsides and the insides, when we multiply and combine, will generate 0 because they have opposite signs. This one would give us 3 of those roots, this would give us negative 3 of those roots. We add them together and get 0, and then our lasts will give us a negative 9. On the bottom, I'll have a t squared times that root. Now notice that the plus 9 and minus 9 will cancel, And once that cancels, I'm left with a t squared divided by a t squared over times this. So I can also cancel the t squareds, and I will be left with the limit as t approaches 0 of 1 over that square root of t, might help if I don't mess up, t squared plus 9 plus a 3. So if I now compute my limit by doing direct substitution, which I can do because I've eliminated that division by 0 that was causing me grief at the beginning, I will get a 1 over a root 9 plus a 3, which will give me a 1 over 3 plus 3, or 6. So now, with this particular function, I'm not real clear on what that looks like, so I'm going to go to my calculator. We notice here I have put in the expression here using x's instead of t's, and what I'm going to use is my knowledge that the y-coordinate of that whole should be about 1/6 when the x-coordinate is 0. We've figured out that we possibly have a whole since we were able to fix the problem that verifies that it is indeed a whole. And so I'm going to adjust my window so that I can see that point, that ordered pair 0, 1/6. So to do that, I will go to the same place that window was on my TI-83s and 4s, except it's buried with the diamond. So I'll go diamond window, and I'm going to let my standard window -10 to 10 be my x values, but now on my y values, I'm going to go from -1/3 up to 2/3, because I want to make sure I can see that 1/6. So I can do a -1/3 here, and I can do a positive 1/3 here. Now if I graph by doing diamond graph, which is diamond F3, we can see that picture. Now what the calculator is doing is it's connecting that hole, but we can verify that it's the location of a hole by tracing to 0, and we can see that there is no y-coordinate because 0 is not in the original domain. But the picture of the curve looks an awful lot like this, which doesn't have a hole at 0. So this graph is going to match this one exactly except at 0, and at 0 we'll have a hole, so there's no y-coordinate here. Now if we trace to the left and right of 0, we should see that 1/6 coming out at. So here I'm still on trace. Let's go to -0.01, and we can see that 1/6 coming up right here. We could also go from the right and see the same 1/6. So over here we can draw the picture in our notes to verify that our picture looks something like this with a hole, and the y-coordinates of that hole are 1/6 when the x-coordinate is 0. So now we'll move to type 2, which is we want to compute limits at the joints of piecewise functions. And those piecewise functions, if you recall, can either be explicit, where we have the curly braces and the branches given to us explicitly, or they can be in disguise. So both of these are explicit ones, so we'll go through those like you will do every explicit function. Analytically, as we're approaching that joint, what we have to do is look at the limit as we approach the joint from the right and as we approach the joint from the left. And our hope is that we will approach the same value from each side. So this says I want to approach 1 from the right-hand side. That means I need values of x to be a little bit bigger than 1. So I come back at my branches and I say, okay, which of these branches am I going to use if x is a little bit bigger than 1? Well, something bigger than 1 does not equal 1, so that means I would be in this top branch. Notice here that this is just a polynomial branch, so direct substitution causes me no grief. I can just plug it in and I'll get a 1 plus 1, which is 2. Now if I want to approach x from the left-hand side, again x will be a number close to 1 but not equal to 1, so I am going to be in this branch again. I plug in 1, and again I get 2. because these two limits match, I get the limit as x approaches 1 on that piecewise function will be 2. So what's happening graphically? Graphically, this says, as long as x does not equal 1, I'm going to be on the graph of x plus 1. So I will look like a line that has a y-intercept of 1 and a slope of 1 and a hole at x equals 1 and whose y-coordinate matches the limit. Now this branch says when x is equal to 1, I actually get an output of pi. So that means way up here at 3.14, etc. So the graph of my function is going to look like this. But notice if I hop left and right of 1 and travel toward the 1, the y-coordinate I'm getting close to is that 2. So that's why my limit is a 2. If we look at the next one, we want to approach 5 from both sides, and 5 again is the location of the joint because I switch branches when x changes from one to the other. So I need to examine the limit as I approach that joint from the right-hand side and the limit as I approach that joint from the left. Now only if these two limits are the same am I going to say that I have a two-sided limit. So if I'm approaching from the right, I need x values that are a little bit larger than 5. So I go look at my two branches, and I see that in this top branch, x is larger than 5. So that means I'm going to be computing the limit on this branch. For the next one, as x is approaching 5 from the left, I need values of x that are a little bit smaller than 5. So I read through my branches, and I see here that x is smaller than 5. So that means to compute this limit, I'm going to use the bottom branch. Now with both of these limits, computing them involves direct substitution. I always use that as my first line of defense, and I see if it works. So I approach 5, that's going to give me the square root of 0, or just 0. Here, if I plug in 5, I'll have a 10 minus a 10, which again gives me 0. Notice I got the same limit for both. So my overall two-sided limit will be 0. If we want to verify that with a graph, we can see here at 5, 1, 2, 3, 4, 5. When I plugged 5 in, I got a 0, but I'm not defined there, and the rest of it's going to look like a root curve that has been moved to the right 5 units. The second branch is the equation of a line that has a y-intercept of 10 and a slope of negative 2. And I get to stay on that line as long as x is less than 5. So my picture looks like this somewhat. It's a little hard for me to draw on my tablet. And we can see if I go from the left and from the right, I'm going to be approaching that same y-coordinate of 0, even though it is not an output on the original function. With these next two variations on the theme for type 2, we have two piecewise functions that are not given to us explicitly. They are given to us hidden. So you need to know that absolute values are just piecewise functions in disguise, as are the greatest integer functions. So let's deal with this absolute value function first. I'm confident that back in your 7th grade, maybe even earlier, you learned what that notation meant. So if I had, say, the absolute value of 17, you knew that nothing happened to the 17 because it was positive. Or if I had the absolute value of negative 3, you knew that would end up being 3. So what you were taught and what you probably rehearsed is that the absolute value just leaves things alone or it changes its sign. So what does that mean explicitly in the algebra world? That means that if you have the absolute value of x, it's actually two branches. We have that inside being left alone whenever the inside is positive, or we have the opposite of that inside whenever the inside is negative. If we graph this using what we've learned with our piecewise function graphing, we'd have y equals x, which is this graph as long as x is greater than 0, or we'd have y equals negative x, which is this graph, whenever x is less than 0. So here's that v you saw in Algebra 2 and pre-calculus, and here's the behavior that you probably didn't have explicitly in your earlier classes, but you were using it without writing it explicitly. So what you need to realize is that absolute values do one of two things, which is why we have two branches. And the two things that we do are we either leave things alone when the inside is positive, or we take the opposite of the inside when the inside is negative. And how we take its opposite is we multiply by a negative 1. So if we apply that to this particular problem here, let me erase this for us. Then we can rewrite this function as a piecewise function. It will be the inside left alone whenever the inside is positive, or it will be the opposite of the inside whenever the inside is negative. Now notice that on my definition earlier I had an equal sign under here, and on this one I do not. The reason I don't is because 3 is not in the domain of this expression. If I plug 3 in, I'm dividing by 0, so I cannot have a definition for this function at 0, because there will be no output. If I simplify this now, we can see that x minus 3 over x minus 3 will just be 1, as long as that denominator doesn't equal 0, and the inside of our absolute value was positive. Here, if I simplify, I'll get a negative 1, which will happen when x is less than 3. So what does that mean for us graphically? It means that at 3, I'm going to see a change in behavior. When I'm earlier than 3, I will have a y-coordinate of negative 1. And if I'm larger than 3, my y-coordinate will be positive 1. So jumping on this curve to the left and right of 3, we can see that I'm approaching two different values. So the limit as x approaches that joint of 3 from the right versus the limit as x approaches that joint of 3 from the left is going to generate two different values. If I want to come from the right, I'm dealing with this top branch, which is 1, and my y-coordinate coming from the right is just going to be a 1. If I'm coming from the left, then I'm in the bottom branch, and I'm on the curve y equals negative 1. So that y-coordinate I'm getting close to is negative 1. Since these two do not match, we say the limit as x approaches 3 on that original function does not exist. If we look here at type 2 example 2, it's another piecewise function in disguise, and with this particular one, if we remember that greatest integer function, it has an infinite number of pieces. So writing it with the curly braces is going to be really time consuming because we'll never finish. So instead, what we're going to do is we're going to look at the graph. And if you don't remember the graph, this greatest integer function takes anything that is not an integer and smashes it down to the integer below it. Things that are already integers remain integers. So if I plug 1 in, I'll get a 1 out. If I plug 2 in, I'll get a 2 out. If I plug 3 in, I get a 3 out. Now as long as I'm in between those two, I get shoved down to the integer below. I don't get to pop up to the next step until I hit the next integer. Oops. Should be down here, sorry. This one is at negative 2, negative 3, and negative 4. So once I have the picture drawn, it becomes much simpler to compute the limits. This says, what are the y coordinates on this greatest integer function getting close to as the x coordinates approach 2 from the right? So I find the 2, move to the right, hop on the curve, and then travel toward 2 to see what my y coordinate is. And I can see that that one will give me a 2. For the next one, I want to approach 3 from the left-hand side. So I locate the 3, move to the left, hop on the curve, and then travel toward 3 and backtrack to see that that y coordinate is still a 2. If I want to approach negative 2 from both sides now, that means I would need to be on the left and on the right and travel toward 2. Notice that my arrows are not approaching the same y value, so this one does not have a limit. Here are type 3 problems where we end up with limits that cannot be fixed. Problems that are issues that factoring won't help, piecewise won't help. We're kind of stuck. So in this case, we will either have an oscillation or we will have an asymptote. So what we need to do is identify those analytically so that we recognize them when we see them. Recall that our first line of defense is to simply plug in that limit and see what happens. So if I plug in a 2, I'm going to get a 1 over a 2 minus 2, which is a 0. This right here is evidence of an asymptote. The reason I know it's an asymptote and not a whole is that the top is not 0 at the same time as the bottom being 0. We also know that it's not an oscillation because that 1 over 0 is not trapped inside a trig function. So as long as we're not in a trig function, those will be the only oscillations that you'll encounter. So we know that this is an asymptote, and because it is an asymptote, we know that the limit will either be positive infinity or negative infinity. There's really no other option. So what we need to do is identify it as an asymptote and then just examine the sign. So if I'm coming from the right toward 2, the top is going to be always stuck at 1, which is a positive number. On the bottom, as I'm approaching 2 from the right, that means this value of x is going to be a little bit larger than 2. So something larger than 2 minus 2 is going to give me a positive number. So that overall result tells me that as I travel toward that asymptote from the right, I'm going to end up heading toward positive infinity. So if I look on my calculator at the graph, I can verify that as I approach 2 from the right-hand side, the graph will head up. If I look at my next one, I want to approach 3. Remember, my first line of defense, as long as it's not a piecewise function, is to simply plug 3 in. If I plug 3 in, I end with a 3 over a 0, which is a number over a 0. It's not a 0 over a 0, so we know that it's an asymptote. There's no trig involved, so that means graphically I'm going to have something funky happening at 3, and it will be manifested as an asymptote. So as I approach that 3, notice that I'm approaching the 3 from both sides. Because it is an asymptote, I have two options. I can approach from the right, or I can approach that limit from the left. Or excuse me, that 3 from the left. Again, I know it'll either be a positive infinity or a negative infinity because I've determined that I have an asymptote. So I really just need to examine the signs. As I approach 3 from the right, might help if I actually come from the left here. If I approach 3 from the right, that means I've got a value bigger than 3. So the top will be getting close to positive 3. The bottom will be something larger than 3 minus 3 is a positive. So that means coming from the right, I'm going to head up. If I'm approaching 3 from the left, that means the top is getting closer and closer to positive 3, only this time on the bottom I'll have something smaller than 3. So something smaller than 3 minus 3 is going to give me a negative number. So I'll end up heading toward negative infinity as I approach 3 from the left-hand side. Because my thumbs are going different places, I write that this limit, as I'm approaching 3 from both sides, does not exist. Technically, the limit doesn't exist regardless when you have an asymptote, but writing does not exist gives you more information. It tells you that your thumbs are not both behaving the same way. So if I had put an infinity, that would have meant that both thumbs were heading up. If I'd put a negative infinity, both thumbs would have been heading down. But because I had one thumb going up and one thumb going down, that means that the limit does not exist. And that's the notation I would use to emphasize that. The next example involving this asymptotic behavior is part C. And the reason we can recognize this as an asymptote is because when I plug -5 in, remember we tried direct substitution first, we end up getting a number over 0, and numbers over 0 are evidence of asymptotes provided we're not stuck inside a trig. And since there's no trig here, we know we have an asymptote. Because we know we have an asymptote, we have to evaluate what happens on the left and on the right to see if we're going both up, both down, or if we're fighting each other. So we will look at the limit as we approach color here. So I'm approaching -5 from the left or from the right. So if I come at it from the right, then that means the top will be getting closer and closer to a -3, which is a negative number. The bottom, coming from the right, that means it's like a -4.7 plus 5. That gives me a positive value. Squared is still going to be positive. So my overall result is -infinity. So coming from the right, the graph will be heading down. If I look at that limit as I'm approaching the -5 from the left-hand side now, then on the top I'll be approaching that same -3, and on the bottom I will be approaching 0, but it will be 0 from the left-hand side, because plugging something smaller than -5 would be like a -5.1 plus 5 gives me a negative number, but then I square the negative and end up positive. So I end up with an overall result, which is a -infinity. So that means coming from the left, I'm also heading down. So since both thumbs are heading down, I can say that that limit as x approaches -5 from both sides is going to be -infinity. So what happens if we don't have a direct substitution that works, or we don't get 0 over 0, so it's not a whole? We're not at a joint that we can evaluate, nor do we have an asymptote or an oscillation. When that happens, our final last-ditch effort to compute a limit is to use a theorem called the squeeze theorem. And the precursor to that is this first one here, which says if the outputs on F are always less than or equal to the outputs of G when X is near A, and the limits of both F and G exist at A, then the limit on F is going to be smaller than the limit on G. So graphically, that tells us if we have an F function that is underneath a G function, then computing a limit at any value of A on G and F will end up with a limit on on F that is smaller than the limit on G. So hopefully this kind of makes sense. It says the y limit or the y coordinates you're getting close to on F are going to be smaller than the y coordinates you're getting close to on G, simply because the y coordinates on F are always smaller than the y coordinates on G. So what does that mean for us when we get to the squeeze theorem, and how does that actually help us when we're dealing with problems? Well, the squeeze theorem takes it one step further, and it says that if I have 3 curves now, I have an F, I have a G, and I have a than G, bigger than F, and I've got a limit on F that is L, and I have a limit on H that is also L, and G is trapped in between them, then the limit on G must also be L. So how does that help us? Well, let's look at an example. So here we have an example that involves this squeeze theorem, because if we try to compute, sorry, I somehow dropped my x equals 0, so add that into your notes. If we try to compute this using our direct substitution, we get 0 times the cosine of 3 over 0, and we see a division by 0 that's causing problems. We also see something that can't be fixed because the 3 will never cancel that x on the bottom, and we're trapped inside a trig, so we suspect there's going to be some sort of oscillation. So how do we deal with this when we can't solve the problem that's caused by that division by 0? Well, what we do is we think about what we know about cosine. Cosine, no matter how we look at it, is always going to be trapped between, might help if I graph it properly, always trapped between positive 1 and negative 1. So we can say that that function x cubed times the cosine of 3 over x will be trapped between negative 1 times an x cubed and positive 1 times an x cubed. That means, graphically, this curve will always be between the x cubed curve and the negative x cubed curve. So if we can compute the limits as x approaches 0 on all three, should be able to compute the limit altogether. So we know with this one that 0 doesn't cause a problem, and we simply get a 0. Same thing here, I can plug 0 in and I get a 0. So this function here is always going to be trapped between 0 and 0 as x gets closer and closer to 0. So that means my limit will be 0. Now I verified this graphically by looking at the calculator. If we go in here and we examine our y1 is being x cubed, y2 is the original function, and y3 is the opposite of x cubed, and I graph it, I have chosen a window that kind of illustrates it. Actually, let me regraph so that you can see it as it tracks through. Here's my x cubed function. Here's that x cubed times the cosine of 3 over x, and then here is my negative x cubed. Notice that the oscillating function is trapped between the negative x cubed and the positive x cubed. And because it's trapped, as I travel along the x cubed, getting closer and closer to 0, and as I travel along the negative x cubed, getting closer and closer to 0, that trapped function also must get closer and closer to 0. So what I'd like you to do now is compute or calculate the limits for the remainder of your web exam problems, and then discuss with each other, or come to class prepared to discuss with each other how you decide which method you're going to use. Are you going to graph things? Are you going to analyze? Are you going to do the squeeze theorem? How are you going to tell the difference between asymptotes and holes and oscillations and joints? So be prepared to discuss that tomorrow.